answers. Anyway, so last time we left off with the scalar product, where we took the dot, we called it also the dot product. We took the dot product of two vectors, and we said one interpretation is that the dot product is a measure of how much two vectors point in the same direction, because it kind of combines the projection of vector A on vector B and the projection of vector B on vector A. So it gives you this sense of how much they point in the same direction. There's another operation. So the dot product operation results in a scalar, just a quantity, scalar. There's another product multiplication definition between vectors. We call that the vector product. Why? Because it results in a vector. Okay? So you could call it dot product and cross product, or scalar product and vector product. If you use the nomenclature scalar product and vector product, you'll remember that the scalar product results in a scalar, the vector product results in a vector. For two vectors A and B, we're going to use the symbol, the multiplication symbol, to denote the vector or cross product between two vectors. And it's pretty simple. This thing, if you have two vectors, let's say in a plane, in the plane of the board, A and B, the vector C is a vector that points in or outside of the plane of A and B, okay, depending on the order of the multiplication. And you use the right-hand rule to do that. Okay, so A cross B, we're going to start with A, and we're going to go to B. So that is going to do a rotation this way. So the resulting vector C is going to point into the board. Why does it look like this? So think of this as an arrow, and you're looking at it from behind. You have the edge of the arrow, and you have the point, right? So A cross B is going to give you C, and that's a vector that points into the board. Or if you do, or now B cross A is obviously negative of the other one. And so let me draw that again. Let's call that. Let's do A and B. And so A cross B is a vector. Sorry. I made a mistake here. Yeah. Okay. Is a vector. So A cross B is a vector C that points outside of the board. In this case, A cross B is a vector that points into the board. That's the bottom of the arrow. Okay. Now, so how do we get the components of A cross B? Okay. There's a full formula for that. Okay. So actually, let's written that down. Okay. So one little thing, before we get into the components of A cross B, there's one little feature that allows us to make deductions about vectors when we're using the cross product. And so when two vectors are perpendicular, if A is perpendicular to B, we said that A dot B is equal to 0. When two vectors are parallel to each other, we have their cross product is equal to 0. Okay? So the cross product is typically, we use that when we're calculating moments in 3 dimensions. Now for unit vectors, so if we take the, you should be familiar with all this stuff. We're just going to go I, J, and K. So I cross J, we're going to go from I to J. Okay. I cross J is going to give us the vector K, right? J cross I is going to give us the vector minus K. So J cross I is going to point in the negative Z direction. Okay? And same thing you can do, J cross K. Those will be helpful when we are doing vector multiplications, etc. So J cross K is going to give you I, etc., etc. Pardon me? questions? Okay. Now, and we can get into the interpretation of the meaning of the vector C, or just the, the magnitude of the vector C gives you the area of the parallelogram, etc. I don't think that's really particularly useful. It's just one interpretation of that, of the cross product. But what's more interesting is when we get into vector calculus. Okay. So we're done with vector algebra. Now we're going to start with vector calculus. Vector calculus. And so this is where we're going to start using concepts from infinitesimal and integral operations, and we're going to apply those on vectors. Okay. So the first operation we're going to look at is what's called the gradient. The gradient. And we define that by a vector operator that's called, some people call that del, the del operator. It's technically called nabla. So nabla. Okay. And it's just when I say an operator, it means it's, think of it as a machine that consumes something and produces something. Okay. So you run something through an operator is going to produce something to you. So we claim that the gradient operator, it's a vector, and is defined by the operation d by dx, d by dy, and d by dz. And whatever nabla consumes, in this case is going to consume a scalar function. We're going to put that scalar over here. It may consume a vector. We're going to see how we do that. That's going to result in a tensor. But for now, grad phi, that's how I would call it, grad phi or nabla phi or del phi. I would rather use grad phi to be very explicit. I'm going to drop the arrow, but I want you to remember that this is actually, this whole thing is a vector. Okay? This whole thing is a vector, is defined as d phi by dx, d phi by dy, d phi by dz, or d phi dx I plus d phi dy j plus d phi dz. Okay. You will also see the following nomenclature: grad phi. Okay, don't be confused. In your homework, if I tell you grad phi and spell it out like this, it's equivalent to grad phi. Okay, this is all great and fun and interesting, but what does that mean? What does the gradient mean? Now, one thing to point out is that phi in general is a function of x, y, and z. Okay, so it's a three-dimensional function. Okay, but what does the gradient mean? Okay. Okay, it measures, it's essentially, so if you go to the 1D explanation of a gradient, take a derivative, it measures rise over run. Okay, so if you take the definition, this is based on the definition of the derivative, it's just three derivatives. But if we go in 1D and you have a line like that, and if this is your function phi, which is phi of x, okay, phi of x, d phi by dx is, so if this is x and this is the value of phi, so if you go from x0 to x1, at x0 you're going to be at phi 0, and at x1 you're going to be at phi 1, which is phi of x1, right, and phi of x0. So d phi by dx is defined as the limit when x1 approaches x0 for of phi 1 minus phi 0 over x1 minus x0. So rise over run. Okay. So if you move from x0 to x1, how much elevation are you going to gain? Okay, great. But there's something more important about the gradient. So in 1D, in this case, okay, it's a scalar value. The derivative is a scalar value. The generalization of the derivative, specifically the gradient into 3D, is a vector. What's the difference between a vector and a scalar? It has a direction. That's the key point here. So yes, it does measure the steepness and how much rise you're going to get for a given run. Okay, if you move by 1 unit in the x direction, how much rise are you going to get? But it also has a very important property, and that's direction. So the question now, what is the direction of grad phi? Where does it point to? It points uphill. Yeah. Always, always, grad phi is going to point uphill. It's going to point in the direction where we're going to rise. And in fact, we can extend this concept to the 1D case. So let me show you how. Sometimes you get new ideas in the class. You don't write notes on those. Then you don't have room in your notebook to write notes, so you start improvising. Okay, so let's consider the function phi of x equal x. Very simple, okay? Now, what is grad phi? Simply 1, 0, 0, okay? So the value of grad phi, we know it's 1D, but it's a vector that always points in the positive I direction. So now when we plot this, this is x, right? Grad phi is always pointing in this direction, in the positive x direction. That makes sense because if you're at any point here, or there, where is the direction of rise? It's in the positive. You got to move in the positive x direction to go up. Okay, so let's take phi x equal minus x. Okay, and grad phi in this case is going to be minus 1, 0, 0. Okay, so then when we plot that, we're going to get this line. So how do we rise? We're going to move in this direction. So any point you're at, any point x you're at, grad phi is telling you if you move to the left, you're going to go up. Okay? One more example. Now the value of, in this case, in the 1D case, even in the 3D case, the value of the derivative tells you how steep you are. Okay? The value tells you how steep you are. Okay? How much rise you're going to get if you move by 1 unit. The higher the value of the derivative, the larger the rise. Okay? Let's take one more example. Are you done with that other side? Yeah? And with this side? Let's keep this definition here. Okay. So now, I'm going to take another example. I'm going to take a Gaussian. Okay? And just a basic unnormalized Gaussian. So let's say phi of x equal e to the minus x squared. Okay? And if you plot this function, it's going to be a Gaussian centered at x equals 0. This is phi. This is going to look like something like this, right? Okay. So now tell me, how does the gradient point in this case? So if I'm at this point, where does the gradient point? Yes, yep, to the right. What about this point? Same. What about that point? Same, because that's the direction of highest rise. What about this point? 0. It's 0 over there. Derivative is 0, right? Because its slope is 0. Now what about this point? Negative x direction. That point, same thing. Same thing. That's really cool, right? Now if you plot the derivative of this function, which is the gradient, right, or the x component of the gradient, right, it's going to be minus 2x e to the minus x squared, right, 0, 0. Okay? And if you plot this, this is how it's going to look like. The gradient is going to be positive over here, and then it's going to slow down and go to 0. So I'm plotting the magnitude of the gradient here, okay? But it's always positive, saying it's pointing in the positive x direction, right? But it slows down here because the curve slows down. Over here, it's really steep. So you get a sharp rise in the gradient, then it slows down. And in this case, it's going to go negative, and then it's going to slow down at the top, and it's just going to go like this. Okay? All right. Now, we're going to show you how this helps you in multiple dimensions. If you have your laptops, we're going to do some Python jujitsu. Okay? It's okay if you don't know Python, you will learn from these examples. But if you have your laptops, I'm hesitating. On some of them, they say, please hesitate when you get to the bottom. I'm like, okay, what did? Okay. Did you have a question? Yeah. You can postpone that to after class. I'm sure you're great. You have a great joke. Okay. Second. Power on. Okay. Okay. So let's see. This little table is cool. Okay. So now I'm going to drag this little window here. If you have your laptop, go to juno.chpc.utah.edu. That's a little thing that I've been working on with the University of Utah Center for High Performance Computing. And if you've done Python before, who's done Python before? Okay, are you familiar with Jupyter? Okay, yeah. So are you familiar with Jupyter Hub? Okay, so this is Jupyter in a web browser. You don't need to even install it on your laptop. Okay, you just log into this guy, use your unit and password. Okay, so use 07153. You're gonna sign in. Oops, sign in. And it's probably overloaded now by some people. Oops. So then it's going to open up a Jupyter session for you. Okay, so if you've used Jupyter, you don't need an installation on your laptop anymore. Just go to Juno. Juno stands for Jupyter Notebook. Okay, .chpc.utah.edu. And then go ahead and create a new Python 3. So since some of you are well versed, we can kind of get a bit faster with this. Okay, Jupyter. Oh man, time flies really fast. I was hoping to be done with vector calculus today. Meaning of gradient. Okay. Actually, I'm just going to show you my notebook because I need to save some time. So if you want to copy, I can share this notebook with you. It's pretty lightweight. This is the function that we just plotted, e to the minus x squared, and then its derivative, minus 2x e to the minus x squared. But what's interesting here is I'm going to look at the gradient of the function x e to the minus x squared minus y squared. So x e to the minus x squared plus y squared in parentheses. So it's right here, and the jujitsu I'm doing here is just essentially making a two-dimensional grid. But what's important here, what I want you to look at is, so if we go ahead and Okay, so this is a function that looks like this. This is the surface of the function. So think of this as the hill, and it has a valley and a hill. Okay. Now we can, based on our understanding of the gradient, if you are located in the middle of the pit, the gradient is going to point away, upward, and if you're kind of getting close, it's going to go all the way up in that direction. Okay, towards the top of the thing. Now, if you do a projection, it's always hard. You know, when you publish papers, don't do 3D plots. Sometimes they're not really useful. You can't see through. You cannot have a nice overview. Always prefer to do contour plots or 2D plots. So what I'm doing at the bottom here is a contour plot of this same function. And what this is showing is a projection of this two-dimensional function. This is the hill, and this is the valley. And on top of that, I'm overlaying the gradient, grad phi. Okay, this is phi. Then grad phi is d phi dx and d phi dy and 0. So it's got two components. These are just two-dimensional vectors in the xy plane. Now, like I mentioned earlier, if you're in the middle of the pit, you're pointing, you just get away. You know, that's the way out of the pit. You go up. And as you get close to the hill, all the arrows are converging to the top of the hill. Okay, should be evidence enough for you what the gradient means. Now, the implication of this, obviously, for fluids are going to be on the pressure gradient. That's the quantity you hear most about. Okay, so when we say there's a pressure drop in a pipe, for example, pipe flow driven by a pressure drop. Pressure is higher at the inlet, lower at the bottom, at the exit of the pipe. Where does the pressure gradient point to? Points towards the inlet, right? So you have a negative, dP by dx is negative, because P exit minus P inlet P exit is lower than P inlet, so P exit minus P inlet is a negative value. And then that ends up going into the right-hand side of the equations for momentum, and that's what drives the flow. It creates a positive force that drives the flow because it's multiplied by a negative 1. We'll talk about that later. Okay? All right. Great. I'm going to disconnect this now and go and talk about something else. Let me power this off. Okay, power off. All right. Clear? Any questions? Okay. All right. So, okay, the gradient, we took the gradient of a scalar quantity, and that gave us a vector. Now, there's another operation on vectors that gives us a scalar, and we're going to call that the divergence. Okay. So now keep in mind, keep the following in mind: gradient of a scalar, divergence of a vector field. We'll show you in a bit how we take what the gradient of a vector means. It's a legitimate operation, but let's finish divergence first. Okay. So is anyone familiar with divergence? It's a pretty cool concept, and we'll first define what it is, and we'll talk about what it means. Does anyone know what divergence is? Or what the definition of divergence? Yeah, yeah. Yeah, okay. So that's, in the limits of that, you get the divergence, right? Yeah, you're right. So divergence. Divergence of vector field. And I'm going to refer to the velocity. Okay. Again, this operation is actually the dot product of the nabla vector with the velocity vector u, or any other vector. Now, one way to remember this is just simply treat nabla as a vector, okay, with three components: d by dx, d by dy, d by dz. So these are the three components of nabla, and u is u1, u2, u3, or ux, uy, uz. Ux, uy, uz. So what is the dot product? Sum of the products of the components. We learned that last week. Okay. So essentially, it's dux by dx plus duy by dy plus duz by dz, and that's a scalar. Okay, that's a scalar. Now, technically, the definition of the divergence is the limit as the v approaches 0, 1 over v of the flux integral over a surface of a fluid. Okay, so what does that mean? If you have particles flowing in a fluid and they're kind of following different trajectories, etc., just randomly drawing this, and you take a volume over here, and because we're continuous, we're going to be able to assign a velocity vector at every point of this surface. Let's say it kind of looks like this. Now, when you take the integral of this velocity vector, dot it with the unit normal for this surface. So you know what the unit normal is. It's a unit vector pointing outwards. And just sum up all the contributions. What you're effectively doing is saying, okay, I'm going to sum up what's coming in, and I'm going to sum up what's coming out minus what's coming in. That's going to give you a net contribution into this volume, right? I mean, this integral, what is it doing? It's essentially telling you I'm going to, whenever u is pointing in the direction of n, so that's going to be positive. If u is pointing in the direction opposite to n, that's going to be negative. And I'm going to sum all of those numbers and subtract them. And that technically gives you how much mass or fluid you've brought into this volume. As you shrink this volume down, you get to this nice definition of the divergence. Okay. Now, this is the mathematical definition. I'm not going to do the proof, but I want you to have a physical understanding, intuitive understanding what divergence is. Okay? So we'll go back here. We have a few cases for div u. If div u is positive, div u is equal to 0, and div u is negative. And I always want you to think of the divergence as fluid flow. Even if you're dealing with divergences of any other vector, whatever that vector is, could be the heat flux, for example, think of it as fluid flow. So as we shrunk this volume, we were able now to define the divergence at a single point. Okay? So when div u is positive, fluid particles are actually leaving the volume. So if you go back to the integral definition, if this integral is positive, the velocity vector over the surface is pointing outward. So what that means is that the fluid is leaving. Okay? It's diverging. Think of it that way. It's diverging out of that point. Okay? So in this infinitesimal volume over here, remember the integral definition, integral of u dot n. The only way this integral is positive, one way this integral is positive for you to remember very easily, if there's more fluid leaving than coming. Correct? That's the only way. Right? So this is the most degenerate case for div u is positive. Particles, fluid molecules, leaving or diverging. Now the opposite is true. When they're all converging to the point, think again about the integral. The degenerate case is when all the velocity vectors are pointing inwards. So you're bringing in a lot of fluid, you're converging. So the other case is when fluid is coming into this infinitesimal volume, and then div u is negative, particles entering or converging. Div u is equal to 0. Not necessarily steady. Yes, whatever is coming in is leaving. Yep. So let's take this point, and I'm going to draw all these vectors are equal in size. This is the case when div u is equal to 0. You can just add an arrow like this, right? This will be the condition for incompressible flow. Why? We're going to show later that div u actually is the net outflow of fluid volume. Okay? The net outflow of fluid volume. I mean, we understand net outflow of mass, but net outflow of volume, well, we always measure volume flow rate, meters cubed per second, right? So div u is the net outflow of fluid volume. So when you think about it, if div u is positive, the outflow, there's outflow of fluid because it's the net outflow of fluid volume. Div u is negative, there's a net inflow of fluid volume. And div u is equal to 0, there's no change in the fluid volume. What's coming in is leaving. Another explanation, and these can all be proven, okay? Another explanation is that div u actually measures the dilatation of a fluid, a collection of fluid molecules. So when div u is 0, fluid molecules retain their volume. You grab a bunch of fluid molecules together and you track them throughout a fluid. They change shape, but they retain their volume. And that's the condition of incompressibility. You cannot compress the volume, you cannot expand it. When the flow is compressible, then your dilatation is going to be non-zero. Okay? Different interpretations for what that means. Okay? Okay. So let's take just a couple of examples, and I'll ask you what each means. Okay? So I want you to think about the following. And these are equal size vectors here. What is the sign of div u here? Positive, negative, or 0? Pardon me? Negative, yes. Because, well, again, it's like, you're like, how does it div u? Think of it converging versus diverging. If it's diverging, that's divergence, that's positive, okay? Okay, so we saw that case earlier. Fluid is leaving. It doesn't matter if the arrows are equal in this case. So div u is positive. Okay? Okay, what about this case? I have a small arrow here, and a small arrow here, and a large arrow there, and a large arrow there. Positive. There's more leaving because this is bigger. Okay? Yeah. There's more leaving. They're diverging. Okay? Okay. Positive, yes. Okay. Negative. You're starting to get the hang of this. Okay. Let me see. How can I trick you? Okay. It's probably 0. Yes. Okay, I'm out of ideas. Yeah, I mean, but can I just thinking about it? That's what it means. Okay. Now, for us people who do CFD with incompressible flows, we notice that when div u is negative, the pressure is very high because the pressure is going to help us enforce mass conservation. So when the particles are trying to come in together, the pressure is going to balance them out. And when div u is positive, when the fluid is leaving, the pressure is going to tell them, no, 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 you're going to stay in there to maintain mass conservation. Okay, that's kind of as a note on the side. Okay, you've probably never heard someone explain divergence to you this way, but I really like this explanation, and it applies to any vector field. Always think in terms of flow of fluid. Okay, what's the meaning of div u? Now, also to kind of jump the gun, eventually, our mass conservation equation is going to look like d rho by dt equal minus div rho u. Now, just think of what happens. What is d rho dt? The accumulation of mass density, mass per unit volume, okay? Accumulation of mass in a very small volume, okay? So if d rho by dt is positive, then there's flow coming in. D rho by dt negative, there's flow leaving, okay? So what happens in this case, if div rho u is positive, and remember density is a positive quantity, so the sign of div rho u is equal to the sign of div u. Okay, so if div rho u is positive, this means fluid is leaving. So then d rho by dt is negative. So density where fluid is leaving. Okay, and if div rho u is negative, then d rho by dt is positive. So negative particles converging, we increase the density. And if div rho u is 0, then there's no change of density in time, and that's incompressible flow. Well, not entirely. I mean, you can, yeah, incompressible. You can have change of density in space, but not have density change in time. Okay. Good? Okay, great. Now, we have 10 more minutes. And now I'm going to talk to you about the gradient and divergence. One more thing. I'm going to talk about the Laplacian before we get there. Okay. Are we done with this? All done? Okay. And I have a Python notebook on divergence as well, but I don't think we have time to do it today. Now we're going to talk about the Laplacian. What is the Laplacian? Just a symbolic definition. Yes. So Laplacian. And we typically do the Laplacian of a scalar. It's defined as the divergence of the gradient of a scalar, also written as del squared phi. That's defined as the scalar d2 phi by dx squared plus d2 phi by dy squared plus d2 phi by dz squared. Okay? What does this mean from what we learned? So we're taking the divergence of a gradient. Think with me. We said that the gradient points, okay, in the direction of increase. Okay? So let's assume you are in a valley. The gradient is pointing away. Okay? What does the divergence tell you? The divergence is positive because, yeah, pointing outward. So you know that you are in a minimum when the Laplacian is positive, and you're in maximum when the Laplacian is negative. Now, more technically, go back to the 1D case where we evaluate when we are min and max. We take the second derivative, right? Same thing here. And the value of the Laplacian tells you how much of a minimum you're at, right? So you could have multiple minima in a function, right? And how much of a minimum or maximum you have, you can measure that with the Laplacian. Okay?
Is that the magnitude?
Well, yeah, it's the value of this. It's a scalar. So the value of the Laplacian tells you kind of how much of a minimum you're in, more or less.
Like multiple minimums, you could
Possibly, yeah. I'd have to check that claim. I have to check that claim. Okay. Now we're going to talk about gradient of a scalar, gradient of a vector, Okay. So this is just going to be a bookkeeping issue. Okay. So we're putting two vectors next to each other, grad u. Okay. What is that going to give us? Okay. Yeah. So it's going to give us a tensor of rank 2, tensor with 9 components. Okay. Components. So rank 2, 3 to the power 2 components. Okay. Now, how do you? So if essentially what gradient of a vector is doing is taking the gradient of the 3 scalar components of your vector. That's what it does. And combining them, lumping them together into one quantity. That's it. It's a bookkeeping method. Rather than us having to do grad of ux and grad of uy and grad of uz, we just combine them all together and do just one gradient of a vector. What does this mean? I was like, it's a little bit complicated, right, to then try to wrap your head around it. But think of in terms of the individual components. Now, the nomenclature here, we call this a dyadic. Okay? When you put two vectors, yes? Pardon me? No, it depends on, so it depends on this, on what rank your vectors are. Okay, so a vector is a tensor of rank 1. Okay, a tensor is a vector of rank 2. Now, if you take the gradient of that, you're going to get 27 components. Okay, so that's a tensor of rank 3, and so on. So it doesn't depend, well, it doesn't depend on how many vectors you have, but if you take another operation here, you're going to have a higher rank tensor, but we rarely have to do that. Okay? So us in continuum mechanics, we only deal with tensors of up to rank 2. Okay? All right, so going back here, this is called a dyadic, and a dyadic is when you put two vectors next to each other, so A, B, and we can write this as the product of A and B, but this is a special product, so we're going to give it the symbol X with a circle around it. Okay? And again, so this is A times B transpose. So this is where you use matrix vector multiplication nomenclature. Vector nomenclature. In other words, if A is a column vector, you put A as a column vector, it has A1, A2, A3, and then you put B as a row, B1, B2, B3. You all know how to do matrix vector multiplications or matrix-matrix multiplications, right? Okay. So how can we make sure that this is consistent? This is a 3 by 1 matrix times 1 by 3. So the result is going to be a 3 by 3 matrix. Okay. Now, matrix notation. It's a tensor. Okay. We represent it as a matrix. So how do you do this? First row, first column. You take the first row and the first column of this. That's A1, B1. First row, this entry is first row, second column. So you take the first row and the second column. That's A1, B2. And A1, B3 for first row, third column. Now we take, this guy is second row, first column. So second row of the first vector, first column of the second vector, transpose. Okay, so that's A2, B1. And you get A2, B2, and A2, B3. And then A3, third row, first column, A3, B1, A3, B2, A3, B3. Okay. So now going back to grad U, we expect that we're going to have the 3 gradient vectors of each scalar component of U. Okay. It's no different than what we did here. So grad U, you write this as grad U transpose. So you put d by dx, d by dy, d by dz, and into ux, uy, uz. And again, 3 by 1 times 1 by 3 is going to give you a 3 by 3. And so first row, first column, so that's dux by dx. First row, second column, duy by dx, correct? So first row, second column, and duz by dx. So you notice the first row has all d by dx. The second row is going to have d by dy of ux, uy, and then uz, and then dux by dz, duy by dz, and duz by dz. Okay? So this one is grad ux, and this one is grad uy, and this one is grad UZ. Okay, columns. All right, and I have, like, if you can stay one more minute, we will do the Laplacian of a vector. Okay? Yeah. Why? Uy in general is a function of x, y, and z. Remember what we talked last time? Yes, so don't confuse the components of the vector with the coordinates or the independent variables. So again, if u is a function of x, y, and z and t, but u is actually ux, uy, uz, each one of those is a function of x, y, z, and t. Okay? So uy, if it's a function of x, so if uy is the y velocity, but it could change as you go down the pipe, right? So there's a duy by dx. Okay? Now the Laplacian of the vector of a vector, I know I'm keeping you, so thank you for bearing with me. So Laplacian of a vector, you can do this as del squared u or div of grad u, which is a little bit more complicated. I like the del squared u. I'll show you a little trick to do it. It's pretty simple. So just say d2u by dx squared plus d2u by dy squared plus d2u by dz squared, and just simply apply these linear operators to the individual vectors and collect I and j and k components. Okay? So this first one is going to be d2ux by dx squared in the I direction plus d2uy by by dx squared in the j direction, right? Because u, what is u? Is uxi plus uyj plus uzk. So apply the second derivative to each one of those. Okay, so plus d2uz by dx squared, okay, plus the second guy, d2ux by dy squared I, plus d2uy by dy squared j, plus d2uz by dy squared, okay, and then finally d2ux dz squared I plus d2ux d2uy dz squared j plus d2uz by dz squared k. And now you have a vector. Okay? The x component of this vector is the Laplacian of ux, right? And the jth component of the vector, or the y component of the vector, is the Laplacian of uy. And the z component of the vector is the Laplacian of uz. Again, we're applying the Laplacian on the individual components of the vector field. Okay? But it results in a vector. Okay? That's it. That's as far as we're probably going to go in terms of tensors. We're not even going to do Einstein tensor notation. We're not finding. I mean, it may be useful eventually in your research, but I find vectors. If you can do vectors, I find them to be much more kind of intuitive. But these are tensors. So this is a tensor, and while this is technically, it's a vector, right? But it's an operation of it's a scalar operator on a vector, so that's going to give you a vector. Okay? Now, if you remember your undergraduate fluid mechanics, this is actually, for incompressible flow, this is the contribution from the viscous stress tensor, right? But what you did in undergrad, when you looked at the Navier-Stokes equations, what you did was just spell it out. The x momentum had this component, the y momentum had that component, and the z momentum had that component. Okay? In chemical engineering circles, we call this the diffusion tensor, or the diffusion of momentum, because diffusion is a described by the flux of a gradient, which is the second derivative, right? And this is the second derivative, so it resembles diffusion. Okay, but that only kind of shows up for Newtonian fluids. Anyway, thank you very much. I will see you on Monday.